Today's topic is going from a decimal number to binary floating point representation.
The notes in your textbook are really important for floating point. Anytime you're not sure, if my videos don't explain things well, you're more than welcome to read the notes. I've tried to get everything into the notes in as much detail as well. And again, it's fairly heavy math stuff, so it's not always easy. The main things you need to know with floating point, oops, don't want that. The main things that you need to know with floating point representation, so that's what we're studying at the moment, is how do we do floating point numbers. And you basically need to know, how do we put a number, how do we get a number out of floating point representation? So if we've got a bunch of binary numbers that look like this, how do we turn that into a decimal number? How do we get things into floating point? So if we've got a decimal number like 252.367, how do we get that into a bunch of zeros and ones in floating point representation? And the other thing that you need to know about floating point representation are the limitations and accuracy issues. Now, the limitations and accuracy issues I've tried to describe. Essentially, my first video that I did, which goes for 20 minutes and takes ages, talks about how do we get things out of floating point and also the limitations and accuracy issues. We do need to cover a little bit more on accuracy, but that knowledge of accuracy, especially in the Java system, is going to come throughout the year as we do various other activities as well. So I'm not too worried about that now. But what this video is going to focus on specifically is how do we get a number into floating point representation if it's presented as a decimal like that. I'm going to start with a really simple example and then do a more complex one. And the really simple example that I'm going to start with is just the number 0.01. That's a decimal, so base 10. Actually, I might not do 0.01. I might do 1.01. Yeah, let's do 1.01. All right, so I'm going to take this number, 1.01, and turn it into floating point representation. And we'll pick an arbitrary system for this. Every time we're dealing with a floating point system, we need to deal with what's the bit allocation. And so in this case, we're going to have 1 bit for the sign and 5 bits for the exponent and 10 bits for the mantissa. That's the same setup that I used last time. And I shouldn't have to define this, but I'll just make it explicit again that our exponent is always going to be an integer, and so that's in 2's complement. And the mantissa is always the bit starting with 0 point something, 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 something. So our first value there is going to be our half, in theory. But in this case, it should be obvious we've got a bit of a problem, because if my first value, if my mantissa is 0.1, or in this case, if I was trying to do this one, you may remember last lesson that our A value has to be greater than or equal to 0.5. Our first and less than 1. That means that our first digit of our mantissa is always 1. You can look at it straight away. If you see, so we're going to have a digit there. This is a positive number. That's going to be a 0. We're going to work out what our exponent is. It might be something like that. We don't know. But this digit here is always going to be a 1. Yes. Yes. Thanks, Hugo, for your question, and Eddie for clarification. I am recording this, so if you missed the beginning of it, you'll be able to watch from the beginning. I'm also aware that this is fairly advanced for a lot of people watching it. But still, just seeing this system in use is going to be helpful. So in this case, that's the counting from the left, 1, 2, 3, 4, 5, 6, 7. In this case, that 7th digit is always going to be a 1, regardless of what number we're converting. The first digit of the mantissa is the start. So essentially what that means is whatever number we're converting, whether it's 0.01 or 1.01 or 252.36, we're going to be coming up with a binary translation of this string as a series of 1s and 0s, and we always care about the first digit. Essentially, what I'm trying to say is, if we're doing scientific notation, we might have a really big number like 3.6 million, or we might have a really small number like 0.000246. And in both of these cases, if we're putting these numbers into scientific notation, we worry about where's the first digit. And in this case, 3.6 million is 3.6 times 10 to the 6. And this number here, 0.000246, we worry about where the 2 is. And this turns into 2.46 times 10 to the negative 4. And so the point is that in both cases, what we're doing is looking at the string of significant digits and putting that as the mantissa. So it's just the string of significant digits that we need to come up with first. So the first job is essentially, what's the string of significant digits there? What's the string of significant digits there? What's the string of significant digits there? And once we've done that, we've essentially worked out what our mantissa is. All we then need to do is work out what our exponent is by doing it in the same way that we did with scientific notation, work out how many decimal places we've got to get. So let me start by just converting 0.01 into floating point representation using the 1, 5, 10 notation. Oh, sorry, the 1, 5, 10 system. Before we even got to floating point, you'll remember how we turned a decimal number into a binary. This is base 10. How do we do it? And our method for that was, well, we double it and then double it again and then double it again. And each time we just lose track of our 1. So this is going to be 0.02, 0.04, 0.08, 0.16, 0.32, 0.64, 1.28. Now I need to double my 0.28 and I get 0.56. Double my 0.56 and I get 1. Oops, I didn't mean to make that black. Double my 1.56 and I get 1.12. Double my 0.12 and I get 0.24, 0.48, 0.96. How far do we need to go? And the answer to how far do we need to go is, well, let's remember that we're counting about our significant digits. We're turning this into a string of significant digits, sort of like that, starting from the 1. So this is now the first significant value. And remember that my mantissa is having 10 digits in it. So that means I'm going to keep going until I've got 10 digits after that 1. That's going to take a little while, but we'll get there in the end. This is going to be 1.92. And you're allowed to use a calculator for these as well if you want. 0.92 doubled is 1.84. 0.84 doubled is 1.68. How many digits have I got? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I just need to work out what the next digit is. It's just going to be a 1. That's far enough. So my mantissa in this case is going to be 1000001111. That's 10 digits, and that's the 10 digits that I've got in my 1, 5, 10 system. Now, the next thing to work out, or we can do these in either order, but I've obviously got my 10 digits there. I'm going to have 5 digits for my exponent, and I'm going to have 1 digit that goes in here for my sign. And in this case, since we're trying to convert 0.01 positive, my sign digit is just going to be a 0. And now I need to do 5 bits for my exponent. What's my exponent? Well, it's essentially, this is my starting point for my number, but I need to shift this 1, 2, 3, 4, 5, 6. So essentially my decimal place is normally there. I'm going to move it 1, 2, 3, 4, 5, 6 to make my decimal place there. So that's 6 spots that I have to move my decimal place. In this case, it's moving it negative because we're dealing with a small number. So just like with normal scientific notation, we can think, okay, a positive number makes it bigger, a negative number makes it smaller. This is clearly a small number, so we need -6 is my exponent. I just need to do that in 2's complement. Let's remember that +6 is, and we're doing 5-bit 2's complement. So +6 is a 4 and a 2 and no 1s. That's what +6 looks like. 2's complement, I'm going to keep my first 0 the same, my first 1 the same, flip the rest. That is -6 in 2's complement. And so that string of numbers, if I just take out the red lines and write it all as one string, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, that number there is positive 0.01 in this 1, 5, 10 notation. Now, the most important thing to recognize is that this particular number, if we actually worked out, if I went the other way using the skills we talked about yesterday, if I took this and I ask you what's the decimal version of this number, we don't get exactly 0.01. We get an approximation to 0.01. We cannot store 0.01 perfectly. It would be a recurring decimal. The pattern would be fairly complex, but we have stored our best approximation that we can with our 1, 5, 10 bit allocation. If we were dealing with another system that was like 187, then we wouldn't even get that much accuracy. Our accuracy would be 3 digits less. So we'd have to stop there and get 10100001. So the more bits that we've got allocated in our Mantissa, the closer we can get to our approximation of that. Does anyone have any questions about that? I know that that's really tough. There's a lot of stuff going on there, especially if you're not used to any floating point, if you haven't finished watching the video. But go back and watch the first video. It'll make sense. I hope it will make sense. I'll also point out, look, this stuff here is the most, aside from the, this and the machine language or the assembly coding that we're going to be doing in term 2, those two things are what most people find the most technically difficult things in this entire course. So this is one of the most technically difficult things in the entire course. And this is also the most mathematically difficult thing you're doing in the entire course. You won't get any question. So floating point generally is a B standard concept. Sorry, let me go all the way back up here. Remember how I said there are 3 things? There's how to get something out of, and how to get something into, and what are the limitations of the accuracy. You should basically thinking about these 3 things. This limitations and accuracy is a C standard skill that everyone needs to be able to do. Getting things out of is a B standard skill, and getting things into is an A standard skill. So that example that I just did right then of getting 0.01 into this floating point is really an A standard skill. It's only going to get asked at a reasonably high level. If we're doing something like 232.7, I'll do another example now. Let's look at 232.7. How would we turn that into a floating point number? Well, essentially, let's turn this into a binary, just like we would have done previously before we even learned about binary. Let's turn the integer part, 232, which is 128. Sorry, how am I going to do that? Normally, I do 232. I'm going to halve it, and half of 232 is 116. Remainder 0. I'm going to halve 116 and get 58. Remainder 0. Halving 58 gives me 29. Remainder 0. Halving 29 gives me 14. Remainder 1. Halving 14 gives me 7. Remainder 0. Halving 7 gives me 3. Remainder 1. Halving 3 gives me 1. Remainder 1. And then I've got my 1 left over. So 232 is 111010000. That's my 232. Now I need to convert my 0.7, so 0.7 into binary. How many digits do I need? Well, I'm already using 1, 2, 3, 4, 5, 6, 7, 8 digits to store the integer bit, which leaves me only 2 left over to store the 0.7. So how far do I need to go? I'm going to turn that into 1.4 and 0.8, and that's far enough. 1, 0 are my 2 digits. So I'm going to put that on there as a 1, 0 like that. This is going to be my 10 bits of my Mantissa. I need to move my decimal place 1, 2, 3, 4, 5, 6, 7, 8. And so 8 in binary, in 5-digit binary is that. So that's my exponent. My Mantissa is 11101000010. And this is a positive number. I'm talking about positive 232. So my sign bit is 0. Any questions?